this computational problem and reduce it to a combinatorial problem. And my favorite combinatorial problem, NP-Complete problem, combinatorial problem, is the independent set problem. Okay, so let's try to show that independent set problem is NP-Complete by reducing circuit set to independent set. So what was the circuit set problem? You're given a Boolean circuit. You want to know whether there's any input that causes the circuit to output a 1. Now, that circuit can compute a very complex function, but it has to do so Boolean operation by Boolean operation. So let's sort of zoom in and say, what does like a Boolean circuit look like? Well, we've got n Boolean inputs, and then we've got a sequence of gates. Each gate is defined by a Boolean operation that has to be coming in from applying that Boolean operation to 2 previous gates. So even though computation is global, locally it's very simple. It just involves these 2 inputs and 1 output. And that local simplicity is what we're going to be able to exploit in reducing this problem to a combinatorial problem. Now, we won't know what the values of these gates are, but we're going to represent this as part of our graph that's going to code this constraint as a constraint within an independent set. So I'm assuming, okay, I gave a hand-wavy argument that circuit set is NP-complete. So to show that independent set, so I'm assuming that you believe me for this one, and we're using this to show that independent set is NP-complete. And the way to show starting from one problem being NP-complete, to show that another problem is NP-complete, first you have to show that it's an NP, but that's usually fairly easy. The other, the more complicated thing, is that we have to show that this problem reduces in polynomial time to this problem. So to show that a new problem is hard, you have to take a known hard problem and reduce it to the new problem. And it's very easy to get mixed up and reduce the new problem to the known hard problem. That actually doesn't tell you anything because we already know that every problem in NP reduces to the circuit set problem. So reduction in this direction wouldn't tell us anything new. But a reduction in this direction, since any problem reduces to this problem, we could compose those 2 reductions and get a reduction from any problem to the independent set problem. So once you have one NP-complete problem, you can leverage it to get more. And so once we have independent set as NP-complete, we can reduce, say, independent set to 3 coloring, show that 3 coloring is NP-complete, reduce independent set to the load balancing problem, show that the load problem is NP-complete, reduce load balancing to other problems, and keep on going. And so there's this tree of how NP-complete problems were discovered, all via this kind of chain of reduction. So we're trying to map this problem to this simple graph problem, and I'm gonna define the problem again, just so you remember, and also. The first way I defined independent set problem was as an optimization problem. Technically, NP is a class of search problems, so I need to redefine it as a related search problem, but in sort of the obvious way. So the third version of the independent set problem, the instance is a graph G, an undirected graph G, and a number K that's going to be in the range 1 to the number of vertices of G. And a solution is an independent set, which is a subset of vertices, and the constraint are that for every u, v, and I, we don't have an edge between u and v. And the size of I is this input k. So we're looking for an independent set that size k. If there's an independent set that's bigger, then we can just look at any k nodes within it. Okay, so we're asking, is the best independent set of size k or more? Okay. So, given, this problem, I think we just like a couple of checks to make sure that it's in NP. How many bits does it take to describe this independent set?
Log K.
So if we have number, yeah, just size of v bits, because we just have to say for every input, is it in or out? That's one way, or the size of I times log v would be another way if you write down the names explicitly. Either way, it's polynomially related to the input size. Most of the polynomial in the input size. And then the other thing we need to check is that we can just verify the constraint in polynomial time. But here we just have to look for every, how to check the constraint of the constraint hold given I is just from the definition of the constraint. Check for every u and v and I is this edge here. If not, then it meets that constraint. And there are only n squared such constraints. And check to see that we have size exactly k. So just count the size of the set. So those two things are verifiable in polynomial time. This problem is in NP. To show that it's NP-complete, we need to take a known NP-complete problem, like circuit set, and reduce it to the independent set problem. And in this reduction, we said there's some kind of three ingredients. First, we have to say how, given the circuit, we create the graph. Because in this problem, there's no graph whatsoever. We need to create the graph, and we need to pick this value of k. And then the second two ingredients, we have to say, if we find an independent set, how does that give us a satisfying assignment? And the final thing we have to say, given a satisfying assignment, that's going to give us an independent set that size of exactly 3. So we'll make sure that when we do this construction, independent sets in the graph that we construct are sort of in one-to-one correspondence with the satisfying assignment of the circuit. And so our graph that we construct has to, in some sense, code the computation in the circuit. So, what I'm going to have is, so for each gate, GI, I'm going to have, we're going to insert 2 nodes, say AI and BI, in the graph. And AI and the interpretation is that AI being in our independent set is going to correspond to BI equaling true, and BI being in our independent set is supposed to code GI is false. So exactly one of these two are supposed to be in our independent set. Then, for computation gates, this is going to be true even for the input gates. I'm also going to have like, or intermediate gates, okay? And so they're going to correspond to like collecting the values of Gj and Gk so that we can perform the operation. So Ci is going to collect so Ci is going to be like Gj equals Gk equals 1. Di is going to stand for Gk equals 1, Gk equals 0, Ei for, say, 0, 1, and Fi for 0, 0. Okay? Note that this is, I is the gate that we're trying to compute, but these refer to the input gates for Gi rather, these values are about the input gates for Gi rather than the output gate.
So are you constructing a new graph?
So we're constructing, so here we just have a circuit, no graph at all, and from that circuit we're constructing a graph. The circuit is defined by, for every gate, it tells us what the input gates are and what operation is being applied to those input gates. So this might be, you know, Gi is the XOR of Gj and Gk. Okay, or it might be Gi is just the negation of Gj, and I just have the Gk in to make things uniform. Okay. So it can be any kind of Boolean function on these two inputs. That determines the circuit. From that, we have to describe a graph. So our reduction gets to say how we transform that circuit into a graph. And so we're allowed any way that we want to. Okay. So this is just my way of doing it. There might be many other ways of constructing a graph on the circuit as well. But I just want to, but somehow we have to code what's happening in the circuit, the computation in the circuit, with what's happening in the graph. Okay. So, okay, so let me, so say that we're trying to code that so we're trying to like compute the correct value of, say that Gi is the AND of Gj and Gk. Okay, so Gi should be true if Gj and Gk are true. But this construction sort of works for any operation, not just AND, just to be concrete. What we're going to have are these two input nodes that are going to code is Gj equal 1 or Gj equals 0, Gk equals 1, Gk equals 0. Okay? So if one of these is in our independent set, then the gate has the corresponding value. Okay? And I'm putting the edge between them so that we're not assigning the gate in an inconsistent way both the values 0 and 1. Okay? And we're going to put in the size, make sure the size constraint is big enough that if we don't have either, that we have to put at least one of these two in for every gate. Okay. So does this make sense? Okay. So now I want to say, okay, well Ci is supposed to represent Gj equaling 1 and Gk equals 1. Okay. So I want to make sure that I can only put this in the independent set if those two things are true. So if Gj equals 0, I don't want this one in the independent set. So where should I put the edges between this layer and Ci? So if we want an edge between Ci and I think flip that, because this would say if Gj equals, if I put an edge between this and Gj, if I put this edge in, this would say if Gj equals 1, I can't have this edge. But instead I want to say if Gj is 1, I must have that edge. Yeah.
I kind of forgot what the objective of circuit set is, so I'm not sure what the independent set represents.
Okay, so the circuit set problem is right here. So we're given a Boolean circuit. Okay. The Boolean circuit has inputs x1 through xn, and it has intermediate logic that's a series of steps where each step is an operation performed on two previous steps, on the outputs from two previous steps. Okay. So like at the beginning, and I made the inputs wires so we didn't have to say or input. Made inputs also gates, so that this handles the case when one of the inputs is an actual input to the circuit. Okay. But it has to be previously computed things, which is why J and K have to be less than 1. Okay. And the challenge is to find an input that causes the circuit to output 1. Now, at the end, we're going to have to put something in our graph that causes the, that says, and the circuit outputs 1. But in the middle of our graph, we just want the maximum independent set to correspond to computations of the circuit on some input. So, does that make sense? Sort of. Let's go through the reduction and see, and then maybe work out an example in more detail and see if it makes more sense. So, okay. So we don't actually want this edge in because we want, if Gj equals 1 and Gk equals 1, we want this to be a possibility. So what is inconsistent with this?
Goes up 0.
If there's 0, and that is here and here. So this one we would connect to Bj and Bk, saying if either of those is 0, we don't have this. Okay. And then, and then this one was supposed to be 1, 0. So, so what two nodes would be inconsistent with this one? Bj or AK. And this one's supposed to be 0, 1. So sort of the reverse, AK or BK. And then this one is supposed to be 0, 0. And so that's going to be inconsistent with AK and inconsistent with AJ. Okay. So now you can see, okay, and we can make, just for double check, we can make sure that we're only allowed to pick one of these, but we're, putting in a complete graph if we want to, but really we're only going to be, there's only going to be one that's consistent with both. If we have one here and one here, that's in our independent set. Yes.
So Ci represents the Gj1 and Gk is 1.
Right.
So I think that everything else which is not 1, 1 input should be inconsistent. Like why exactly just the
Yeah. So, but we have to assemble that, because here we have something that codes that Gj is 1 or Gj is 0, and here we have something that codes Gk is 1 and Gk is 0. So we have to take those two bits that are sort of coded in separate places in our graph and put them together in the same place in the graph. because that's what this little gadget does, right? Because it says GJ is 1 and GK is 1. GJ is 1 and GK is 0. Okay. And we can put in the complete graph to make sure we're not putting in more than one of these possibilities, but I think it's actually redundant, but it's also harmless. So we might as well put in all the edges between them. Sorry, does that answer your question? GJ and GK are sort of represented separately, and now we want to have them represented together. And now we can say, okay, well now GI is supposed to be the AND. So the AND being true corresponds to which of the cases below it? Just CI. Okay. But that means that if we want it to be, we want to be able to pick this if CI is true, if CI is picked, but not able to pick it if any of the others are picked. So which nodes should we connect this one to? D, E, and F. So if any of these cases are true, the AND is not true. So this says if we pick this one, we're not allowed to put this one in our independent set. Okay. On the other hand, this one says the AND is false. What's inconsistent with the AND being false? Just 2 being true. So we would just have the one edge here. Okay. You note that this part of the gadget is the same no matter what the operation is. This top part depends on the operation. Okay? An OR would be different. If this gate were the OR, we would connect the yes to anything where the OR is false, which would only be FI, whereas we connect the no to anything where the yes, to anything that represents a case where the OR is true, which in that case would be CI, DI, or EI. And there, other operations would have other subsets, but each operation would correspond to a fixed subset, and we could just get which subset by applying the operation. Okay. So we're going to do this for every node in our graph. Okay. Okay. Until we get to the end, we'll have AM that represents, we'll do this up to the end. We have AM that represents gate GM being true. BM represents gate GM being false. So what defines something being a satisfying assignment?
AM must be true.
So this gate must be true, which means that then we'll just delete this node. So we'll do that whole gadget, but at the end we'll delete this BM node from our graph. Okay. Yeah.
Out of curiosity, this is sort of an artificial construction, but what it says is sometimes that any graph can be interpreted as a circuit.
No, it says any circuit can be interpreted as a graph.
Sorry. Okay.
So that's a good point. Because it's an unnatural construction, very few graphs actually look like this, right?
Yeah. Okay.
So when I'm not like chiding you for the question. I want to use it to make a point, which is that typically the image, the range of a reduction, you're proving something's NP-complete, but the kind of instances that you've proved are hard are typically very strange instances. They don't look like, I'm overusing the word typical, but they don't look like typical instances. So you've shown that there exist hard instances of the problem. You haven't shown that every instance of the problem is hard, and it doesn't follow that the instances people are trying to solve are hard. And so that's or at least not maximally hard. So So that's one thing that we're going to get back to when we're asking, okay, now our problem is NP-complete, does that mean that we give up on it? And the answer is no. For a number of reasons. Okay, so this is a little bit strange, but seeing that we're actually like coding each step of the computation as this kind of circuit. So maybe I should just do a small example.
How do we choose K?
Oh, now I have to go through and choose K. Good point. Okay. So, what do we want K to be? Okay. Well, we have these two classes of nodes, the AB node and the CDEF node. The AB nodes are there for every gate, including the input gates. The intermediate nodes are only there for the intermediate gates, the ones that are actually doing computation. So they're going to be M total of these pairs and M minus N total of these intermediate gates. This is the number of intermediate operations, because it doesn't include the input. This is the total number of gates, including the input gates. So, of each of the AB pairs, how many, so there are two M nodes. There are two M pairs, so that's a total of two M nodes. There are M minus N, sets of 4, so that's a total of 4 M minus N nodes. But of this pair, how many do we want to be in the independent set? Yeah, just one from each pair. So, so we're going to start with M, so that we have one from each of these pairs. And then, how many of each of these 4 tuples do we want? One. They're inconsistent with each other, so we're going to have, even in the ideal situation, exactly one from each pair, each 4 tuples. So K is going to be this kind of looking a little bit strange number, but it's exactly what we need to force any independent set of size K to have one thing from each of the, that represents each of the input of the wires, and one thing that represents each of the intermediate computations. Yes.
I'm sorry, I'm missing something here. So this is a representation for one of the gates. And you build something like this for all.
So we're going to build this for every gate we build this.
So how do you, it sounds like, it seems like it's, in my mind I'm picturing a disjoint, a graph.
Right.
How do you connect up the...
So the connections are remember these are from the GJ and GK gates. So they're the actual nodes that we constructed as the top part for the previous cases. So maybe I should just give a small example. The problem is that it gets a little messy even for small examples. So let me just see how it works.
Oh, yeah, okay, thank you.
So let's say that the formula is x1 or x2 parity x3 and x1 or, and not x1 or x2. So then we're going to start off just representing each input as a pair of gates. So then, yeah, I'm already regretting this. Because, okay, so let's say that the first thing we do is compute this we want some intermediate gate that says not x1 4x2. So this is going to be our G3, is this expression. So we'll have C3, D3, G3, F3, A3, B3.
We would use one
Yeah.
logical operation, right?
This is one logical operation.
Wait a second at the end.
So but, you know, for every logical operation, we're going to have 6 nodes. Okay, that's our construction. Okay, well, 6 is a constant, so but for writing on the board it gets big. So we said C3 is connected to B1 and B2. C3 is connected, let's say for 1, 0, E3, F3, something like that. Sorry. Oh, this is what people were saying. This is number 4. Sorry, reverse. Okay, and now we're doing something's not x1 or x2. So not x1 is true. Okay, this is false if x1 is true and x2 is false. So D4 is the only case when this is not supposed to be true. And then B4 corresponds to the other. So now, so far, we're going to be selecting A4 if this intermediate case turns out to be true. We're free to select one of A1, A2, A3, B1, B2, B, one of A1, B1, one of A2, B2, one of A3, B3. But whichever one we select is going to percolate up the tree, up the graph, and force values of the other gates. Of the other nodes, I should say.
So I was going to command A4, B4 to B3 for the next step.
That's right. Well, so first we have to do these intermediate operations. So we're going to have like an A5, B5 that's going to represent the parity. Okay, so maybe I'll just remove this one at least. So now we'll have A5, B5, 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 F5. They'll be connected, this will be connected to these 2 nodes, this one's connected to this one, these 2, this one's connected to these 2, and this one's connected to these 2. And then we say, well, now the operation is exactly 1, so this is false if both are true or both are false. So this is this F and C are the ones that rule out A. D and E are the ones that rule out B, and so we'll connect them like so to represent this operation. Then we'll put in, to represent this final AND, we'll put in another level of CDs, E's, connect them to these 2 in the same pattern that we have below, and then we'll just have the 1, since this is the output gate, we'll just have the A, not the B, and that'll be connected to anything that would make this AND false. And I'm getting, let me just first sketch that. So we have the C6, D6, E6, F6, and it's going to be connected in the same pattern as both to the 4 and the 5, as before, because gates 4 and 5 are the inputs to the output gate, but then we only have an A6, and that was, what was it? It was in Word and, I forget which, let's say it's in the end. And, that would be connected to any of these three.
So which parts correspond to which parts then? So then,
Very cookie cutter now.
so,
Well, that's the point,
Yeah, right?
right, is that this reduction had better, we better be able to program up the reduction. So the reduction just states isn't like globally analyzing what's happening in that circuit. It just, gate by gate, every gate, it looks at the operation and puts in these nodes. Puts in a little gadget there. And so the point is that locally, the logic is preserved. And so by, induction, globally, the logic is preserved. Okay, so this is, so is it kind of clear what we're doing? Okay. So now what do we have to show about this? We have to say that given, if there's an independent set of size k here, then there's an assignment that causes the circuit to output 1. And if there's an assignment that causes the circuit to output 1, then there's an independent set that achieves the size k in the corresponding graph. Yeah.
But how currently that is reduction polynomial?
Okay, well,
That's the form that is L
right. But what do we do for every gate? So the input is the circuit. It's not the number, the input is the circuit, not the number of inputs to the circuit. So the input size is M, the number of gates in the circuit. And what did we have to do? For every gate, we had 6 nodes that we needed to create. We needed to, and then based on the operation, which is just a finite table, right? 2 inputs, 1 output. We needed to create this fixed graph. Okay? So we needed to put in, some fixed number of edges between those 6 nodes and specified other nodes that were also specified as part of the gate description. So every gate, putting in the corresponding part of the graph is constant time.
So is there a gate that depends on number of them to learn all the inputs?
So no, that's the whole point, is that when you pick apart Boolean logic, it all gets reduced down to these operations on 2 inputs. So there's if we had operations that required huge numbers of inputs and we couldn't get rid of them, make them simpler, then we probably wouldn't be able to reduce a NP-complete problem like circuit set to the combinatorial problem. But because computation can be broken up until each operation is local meaning just constant size, okay, that's allowing us to create this graph. So, okay. So, what we want, then, is to sort of show that correspondence. That was our intuition. That we're going to select the node in our independent set, if and only if the corresponding gate has the corresponding value. So let's say that I is an independent set in our constructed graph. Now, I has a certain structure, so because we picked K to be the number of pairs, and we put edges between each pair, plus the number of these 4 tuples, and I put, just to be safe, put the complete graph between each 4 tuple. Okay? That means any independent set of this size has to have at least 1 from each pair, and it has to have exactly 1 from each pair, and exactly 1 from each 4 tuple, for each group of 4. Since size of value equals K, I has exactly 1 node from each AI, BI, and 1 node from each CI, DI, EI, FI. Otherwise, if it missed one of these sets, it can't have more than 1 because they're all inconsistent with each other. And it can't have less than 1 because then it couldn't total up to size K. So we're going to use that to define the satisfying assignment. So when do we want to set xi to be 1 if
XI is, what is XI?
so where we're going to look, you know, we have some independent set in this graph, like this one. It has like one of these and one of these. Okay, I'm being inconsistent now, but you have some potential independent set. Where are we going to look to see what the actual corresponding satisfying assignment is?
BI or AI or BI?
The AI and the BI. They were supposed to correspond to whether we set the input to 1 or 0. So we should set this to be 1 if AI is in the independent set, and 0 if BI is in the independent set. And we already said that exactly one of these two is going to happen. Okay, so that defines our assignment. And now, what we'll say is that, you know, by induction, I claim that AJ, or for gate I, AI is in the independent set if and only if GI is true on this assignment. And that's really, that follows from how we created this graph. Okay? Basically, we're going to say, well, you know, all those different cases, one of CI, DI, EI, or FI is in the independent set. That one has to correspond to, you know, it's inconsistent with 2 of the GJ, if it's CI, then it's inconsistent with BJ and BK. So if DI is in the independent set, CI I should say, then BJ and BK are not in the independent set, which means AJ and AK are in the independent set, which means that by induction, that GJ was 1 on this input, and GK was 1 on this input. And then, you know, whatever the operation is on 1, 1 is going to be forced to be the output of of GI. Okay. So I'm being a bit hand-wavy here because it's just this huge case analysis saying that we created the gadget correctly, but, it's kind of mindless. Okay. So, but then we have to say, why is the output 1? Which node do we know has to be in our independent set?
Yeah.
AM.
AM, yeah. We deleted the AM.
Yeah. Because we deleted BM. This claim says EM is 1 on this assignment. Okay. So, okay. So, in the reverse direction, we have to say that given any assignment, that gives us an independent set. Okay. So the assignment only tells us what the value is at the leaf. Well, what can we do to get the independent set? We can deduce all the other values by the rules of the circuit. 1 gets A1, 2xn gets AN. Deduce values for each GI. AI is in the AI be in I if and only if GI equals 1, BI in I if and only if GI equals 0, and CI, DI, EI, FI, CI if and only if. Remember, this is going to only be defined when there's inputs GJ and GK. And this was supposed to stand for GJ equals 1 and GK equals 1. Okay. DI equals NI if and only if GJ equals 1 and GK equals 0. And similarly for E and BI. We put them in according to these rules, and because of the correctness of our gadget, then this actually the same relationship is going to hold. Each of these is there isn't going to be an edge between any two as long as it's in the independent set. And finally, we know this is a satisfying assignment, so this means by this construction that AM is going to be in our independent. And we're going to have exactly one of these pair in our independent set, exactly one of these 4 in our independent set by definition. And so the size of the independent set is exactly going to be this m minus n plus m equals k that we're shooting for. So it's almost the same reasoning, it's just we're doing it in reverse.
So we argued that circuit that was NP-complete because we looked at the nature of what the algorithm was and showed
Right.
that
that circuit could basically code any algorithm.
right.
And now we're saying, okay, code that complicated algorithm as a circuit, and now we'll go through that circuit gate by gate and create a graph.
But so is there ever any utility in, or is it, so here this is a very systematic sort of visual depiction of a way you turn a circuit into a graph.
Yeah.
Well, by definition of circuit type being NP-complete, there must be some sort of way to turn any given graph into a circuit.
Yeah, that actually is, you can just do it kind of
Write the
directly.
program and look at the circuit, and look at the,
So how would we reduce independent set to circuit set? We just need to write down a circuit that verifies being an independent set. Okay? So we have one variable for a node. So just the question is, there must exist a way of, so what's an example of how we would reduce independent set to circuit set? The easy part is actually, writing down that something's an independent set. So say that we're given a graph.
It's just a bunch of XORs.
It's not XOR, it's just not AND. So it's just,
Oh, okay.
because it could have 0.
I could,
No, so it's not exactly 1, but it's at most 1. So, independent set to circuit set. Okay. So, so the first thing you need to do is say, okay, well, how we're going to like represent, what are going to be the variables? Okay, for every node, let's introduce a variable xu that says u is in, it's going to be 1 if and only if u is in the independent set. So we're taking each bit of the description and making it a variable, an input variable to our circuit. Okay. So then we write down, for every edge, we're going to write down a constraint that says we can't violate the independent set property for that edge. So it says not xu or not xc. So every edge from u to v, say either this is not in the independent set or this is not in the independent set. And we're actually like taking the Boolean and over all the edges in the graph of this expression. But then the final thing we have to do is a little bit more complicated, although it's kind of an exercise in graph design. We have to say the sum of the xu's is this fixed number k. So there you have to actually like talk about, oh well, we're summing n numbers and we're doing carries and so on, and there's a bit of circuitry in here. But it's not so difficult. And again, you guys think of how we can, came up with this reduction, because well, how do we code a solution as a set of bits? Well, we have one bit per node. How do we verify the constraints? We just check for every edge that these two things are false, and then we have to check that the sum is k. So just sort of writing this down as a, whatever algorithm we use to check, to represent and check a solution gives us the reduction to circuit set. I should say that there are, okay, in addition, or maybe okay. Sorry, what I was going to say, is I wanted to have be the main part of the class, which is, what do you do if your problem that you need to solve for some application is NP-complete?
just write your phone number and just call Russell.
No.
Email?
Okay. That method is what you do if your problem is NP-complete, but you know a phone number from algorithm. Okay. So it says there are like a number of fallback positions. I think the most important one is to go back and ask, is this really my problem? And, okay, okay. I should say, okay, the key word here is this, is problem rather than my. Here's what I mean, is we have some intended applications. And in the application space, we have some actual combinatorial problems that we need to solve. But how do we actually start writing down, describing our problem? Okay. We have to take all the instances of our problem and come up with some kind of formalism that describes them all. So, this is a correct formalism that describes, if these are the problems I need to solve, this is the correct formalism that describes them all, but so is this. Okay? And so, if we define our problem too broadly, then maybe the big circle, it turns out to be NP-complete. But that doesn't mean that the problem that we need to solve is NP-complete. Okay? It could just mean that we drew the formalism too broad. The way we defined our problem, we were too ambitious. It wasn't really the problem we needed to solve. And why does this actually comes up all over the place? Why? Because what we said is, say that the real problem is polynomial time. Okay? Then we can still reduce that problem, easy or hard, to an NP-complete problem. And so, these problems map to an NP-complete problem, which means that there's always a way of viewing our problem as a special case of an NP-complete problem. And that means there's always a way of defining our problem so that it's NP-complete, whether it's hard or not. So the first thing is, defining my problem in too general a way? So for example, take the matching problem. Where we're trying to find a set of edges that don't intersect. Okay. Then we could define a graph whose vertices are edges, and we put in edges if the two edges in the original graph share an endpoint. Okay. Oh, well, solving matching on this graph is solving independent set on this graph. So I need to solve the independent set problem. And I know that's NP-complete. Oh, I'm stuck. But it doesn't really tell us that. So the point is that not every graph, the problem that you really need to solve can be viewed as independent set, but it's not going to be independent set in an arbitrary graph. It's going to be independent set on the line graph of a bipartite graph, which is a very special kind of graph, and maybe we can solve the independent set on that special kind of graph. similarly, they look at some of the event scheduling problems that we're trying to solve, right? Event scheduling is basically you have this graph where you're putting in an edge between events if they intersect. And what we're trying to do is find the biggest set of events that don't intersect, the maximum independent set in this graph. But it's a very special kind of graph. It's called an interval graph. Okay. And problems that are hard in general tend to be easy on interval graphs. Similarly, the event scheduling in different rooms, that was coloring, finding minimum coloring of an interval graph. So if you overgeneralize your problem, you can always make it NP-complete. And that's, like half the time when NP-completeness shows up, it's because you've overgeneralized your problem, not because you really need to solve an NP-complete problem. Okay. So, but say that you've gone back and you've put in every restriction to the input that you can think of, and it still seems NP-complete. Okay? So then you have to say, okay, now I have to actually do something with it. A second kind of thing we can shoot for is, well, maybe we need exponential time, but can we get like an improved exponential time? Is improved exponential time, maybe that's good enough, because my problem's not too big, and maybe if I can get like a factor of 10 in the exponent, then I'll be okay. Okay. And for this, we learned at least one technique in this class, which is backtracking. Now, backtracking is a very simple approach, but it turns out that there are whole industries based on optimized backtracking algorithms. So, for example, so one of the standard NP-complete problems is the special case of circuit set where the circuit is in conjunctive normal form, just a and of ors of variables. Okay. So this is a really good NP-complete problem in two senses. One is that people have really optimized backtracking algorithms, improved exponential time algorithms for the CNF SAT problem. Okay, people have spent their lives optimizing these algorithms, and not just one life. It's like teams of people. Okay, every year there's a competition to solve SAT a little bit faster, and people are making some progress. Okay. The other thing is that in terms of reductions, many important problems can be reduced to 3-SAT. It is an NP-complete problem, so basically, in principle, any problem is reducible to 3-SAT. But sometimes the reduction increases the number of variables tremendously. But with 3-SAT, it has enough expressive power that usually you can come up, or very frequently, you can come up with a reduction that also is pretty parsimonious, doesn't increase the number of variables by too large a factor. That combination means that these optimized exponential in the worst case, but still pretty good 3-SAT algorithms or CNF SAT algorithms actually can be used, leveraged to solve a whole bunch of other problems. I think the most successful uses have been in verification, protocol verification, circuit design verification, and so on, where you have these kind of complicated constraint satisfaction problems that you need to solve. I guess there's been a similar work on integer linear programming which again is an NP-complete problem, but there have been people, it has this kind of sweet spot between there are non-trivial exponential time algorithms for it, and it has a good, the reductions tend to be parsimonious. Usually, you would use like a SAS solver for a purely discrete problem, and ILP when it's a kind of mixture, when you want to use a mixture of reasoning about real numbers and reasoning about discrete values, 0, 1 values, or in a small integer. So, okay. And the thing is, it's known that these algorithms actually take exponential time in the worst case, but they still can actually solve some instances with hundreds of thousands of variables, sometimes even millions of variables. So saying that it's exponential in the worst case doesn't mean it's exponential in your case. So, another thing that you can do is say, oh, the problem is NP-complete. That means an algorithm to solve it is probably going to be exponential time. But maybe you can make it exponential in some parameter in the problem that in your instances is small. Just like I guess my typical example is, say you've got a problem, where it has two parameters. And it comes up from computational biology. N is the number of acids in a sequence in a chromosome, and K is the number of chromosomes. Okay, so say you've got you've shown that this problem in general for arbitrary N and K is NP-complete. Okay, well, there's still a huge difference between something that's like 2 to the n times k, and something that's k times 2, or 2 to the k times n. Okay? Because when you're talking about the number of amino acids on a chromosome, what are we talking about? Millions, potentially billions. I think, like with humans, it's maybe billions. 2 to it is out of the question.
2 to the 23rd or something?
Yeah, what K is 20, I think 26.
26.
2 to the 26. Okay, really the problem is the N rather than the 2 to the K, per se. Because, you still have 2 to the 26 is actually pretty reasonable. It's going to be a smaller factor. 2 to the K times N is going to beat N squared. Because 2 to the 26 is, maybe 64 million. N squared, N might be a billion. N squared is going to be huge compared to that. Okay. So that's one thing we can do is say, maybe, not being polynomial time is okay for us. So what's another thing we could sacrifice and still hope that it might be okay, that we've learned about?
The correctness?
Yeah, so we could approximate, so replace correctness with approximate correctness. So try to find an approximation algorithm. Or find an algorithm that's not too horribly bad. Maybe you don't actually need, maybe it's NP-complete to find the exact value, but if you can find a value that's only 10% more, that's good enough for your application. Or at least it's better than finding one that's not, that's more than 10% more. So like good news is that there are a whole host of approximation algorithm techniques out there The bad news is that for many problems, the best approximation ratios are still pretty big. And the even worse news is that there's been recent advances in theory that have allowed us to prove that for many problems, even finding approximation guarantees that are non-trivial is NP-complete. So sometimes you can do this and it works well, and other times it still doesn't solve your problem because it's still hard. So what else can we try to sacrifice? Sorry?
Randomized algorithms.
Oh, okay, randomized algorithms. Okay, so there's two kinds of things people mean by randomized algorithms. Let me distinguish between the two. There's algorithms that work in every case, but make random decisions, like quicksort. Okay, it works on every instance, and it's fast on every instance. If you actually flip the coin, so there it turns out that having a randomized algorithm that's polynomial time is probably the same as having a deterministic algorithm that's polynomial time. Or at least it doesn't seem much more likely that we'll be able to find randomized algorithms in that strong sense for NP-complete problems than we could for deterministic algorithms. So I don't think that just randomness helps us that much at all. Okay, at least it's, so it does help us, but to a limited extent. Okay. Doesn't really change like where the line is between intractable and tractable problems. Often, randomized algorithms are good to like first start for, randomized algorithms are might save you a small polynomial factor over deterministic algorithms. But there's another thing people sometimes mean by using randomness in algorithms, which is instead of looking at algorithms that make random choices, look at algorithms' performance on random inputs. Okay. So this is like a so I guess like in the 70s, people had this idea of doing average case analysis, but it was kind of disappointing. And the disappointment wasn't that you didn't have, really interesting algorithms and really interesting analysis techniques. It's that you did the average case analysis and it meant nothing. And because the algorithms that worked well on random inputs didn't work well on actual inputs. And the reason is that random inputs, in some sense, look alike. Almost all inputs look alike. Have this kind of same kind of homogeneity. They're very homogeneous. They all, a random graph, every node has about the same degree. As opposed to a typical input, and typical inputs have all sorts of weird structure to them that a random input would never have. So designing an algorithm that works well on random inputs doesn't seem to be at all helpful for designing algorithms that work well on typical inputs. Now there is on the other hand, there is a more recent development, about 10 years old, that's a lot more promising. That's something called smooth analysis. That's kind of a hybrid of worst case and average case. Smooth analysis says, let's start with a worst case input but assume that you don't directly run your algorithm on that input. You know, so this is like what happened in nature is worst case. Okay. But before you actually collect your data, you're collecting your data by doing some statistical analysis of nature or doing some measurements. And everything that you're doing to actually collect information about your data that you're going to run your algorithm on is actually noisy. So a good model of what, you know, typical data looks like is take some worst case real life things and then add some random noise and look at the performance of algorithms on this combination. And so Spielman and Tang started this by giving a smooth analysis for the simplex method that gives a good, sort of gives a theoretical explanation for why the simplex method is an exponential time algorithm to solve linear programming, where we know there are polynomial time solutions, but no one uses them. Everyone uses the simplex method. So why should the simplex method be so good in observed performance? And since then, it's been used, since smooth analysis has been used to give a similar behavior for other algorithms. Finally, you know, although I hate to admit it, so then they're just like heuristics you can use that frequently solve hard problems, but no one really understands why. I'm very interested in trying to, so, you know, some people think of heuristics as beyond the scope of theory. I think of them as challenges for theory. Try to come up with some explanation for why they work, something I'm very interested in, but so far the results have been modest.
Give an example, or a simple example.
Okay, so like a very good heuristic is there's Metropolis and its more sophisticated cousin simulated annealing that do some random search for optimal solutions by using randomness to avoid getting stuck at local optima. So that's one of the algorithms I'd be really interested in trying to understand. I first started getting interested in this when I went to a student's thesis defense, and they said, this problem's NP-complete, so I used a simulated annealing heuristic. I said, well, why did you use the simulated annealing rather than some other heuristic? And he said, because my lab had just bought a simulated annealing package. I thought there must be a better way to answer that question. That was a totally honest answer, but there must be a better way of doing it. Okay, so that's the list.
Oh.